Welcome to Phys3001 Theoretical Physics. Science is, to paraphrase loosely, the collection of things we know about how to find out about the world around us without fooling ourselves in the process. Now, the further we go beyond our usual everyday experience, the harder it is not to fool ourselves, and we have to be more careful. And the reason for that is that our intuition becomes an increasingly unreliable guide. And indeed, the story of theoretical physics over the last century or so has been that we've discovered that the universe is in fact a lot wilder at heart than we at first imagined. But that's not to say that it's inexplicable. Far from it. In fact, science seems to follow, and the universe around us seems to follow, a small set of simple rules. Everything from the stars and everything we see in the night sky, all the way down to those little plastic things that are on the end of shoelaces, and all the way down to crazy subatomic particles that never exist by themselves, all follow a surprisingly small set of mathematical rules. And those rules seem to follow a set of physical principles. This is the first course where we move a little bit past how things behave and investigate more about why they behave that way. In other words, not just what is the theory of the things around us, but why is the theory of that form? And more specifically, we're going to look at some fundamental theories in physics, and more importantly, how they fit together and how they interact. So our three topics are going to be classical mechanics, quantum mechanics, and special relativity. So the first thing we look at is classical mechanics, and we do that because it's a very practical thing to do. This is the realm where we live. It comes up in all sorts of everyday things. And there's a lot we need to know about all of these things. There's a lot we need to know about the realm we live and how it works. The next thing we're going to look at is quantum mechanics. Now, quantum mechanics is the fundamental theory of all things we find in the universe. Large and small, charged, neutral, massive, massless, all of it. Now, we first discovered quantum mechanics when we looked at very little things. Then we look at special relativity, which is the fundamental theory of space-time, which is essentially the canvas on which this enormous painting is displayed. And special relativity is important when things go very fast. So these things tend to come up when we talk about very large things like the cosmos or cosmic rays where things are traveling very fast, or also perhaps when we're talking about very sensitive measurements like when we're using the GPS system, which relies on very careful timing. But there's no reason to think that these categories are in fact distinct. Indeed, we can imagine having a very large quantum mechanical system, or we can imagine having a very small special relativistic system, and we can indeed make these things. And so classical mechanics, quantum mechanics, and relativity are all in fact simultaneously true, and they're just different limits of the same universal theory. And that means that in fact each of these theories relate very strongly to each other. And indeed, when you break down these theories into their fundamental principles, you find that they really shape each other, and all three theories share deep similarities and common insights. Now, this course assumes that you've in fact met classical mechanics and quantum mechanics and relativity before, but we will start from scratch in each one, so it'll just be quite fast early on. Now, you have several learning methods. Obviously, you have these videos. And remember, you can come back over these videos. I strongly recommend, I can't put this strongly enough, when I suggest that you try something, when I suggest you work through something, have a go at it. Make sure that you actually spend your own time working on things that we cover in these lectures. The next thing is that you can go to textbooks. Any good university library, including ours, has perfectly good textbooks on classical mechanics, quantum mechanics, and special relativity. And in fact, those are usually the names of the book. There are a large number of them, there's lots of different treatments, it's all the same physics, so you can just find one that you like. You'll note that we link and reference particular textbooks under our videos, but you should be able to find your own with great ease. Of course, along those lines, there's also a large number of notes on the web, which range all the way from fully fledged free PDFs of textbooks down to particular lecture notes on courses in classical, quantum, and relativity. Now, these are very well developed topics, and so you'll find that even the Wikipedia pages are useful and well explained. When you go from different notes and different books, however, do be careful that notation doesn't change too much. There are a lot of different conventions, and you need to be aware of that when you're dealing with these things. Finally, there's help. Come and talk to me as the lecturer, send me an email, go onto the discussion board, talk to your fellow students, talk to your students in the drop-in tutorials, talk to your fellow students in the workshops, talk to your tutors as well. So we're all very happy to help and very keen, and sometimes exactly the thing that you want is 5 minutes talking with an expert to help get over some particularly tricky problem or issue. So let's get started with classical mechanics. Now, why should we look at classical mechanics again? It might seem that once you've learned Newton's equations, then all you need to do is learn all the forces, and then you can model anything that happens in the universe. Once you know the forces, you know about the electromagnetic force and the gravitational force and so on, then you're done. You just solve Newton's equations and find out what happens. And the answer is, of course, that that's a lot easier said than done. And there are far more elegant and convenient ways of dealing with classical mechanics problems than Newton's laws. And indeed, there are also ways that make our understanding deeper as well. By reformulating classical mechanics using Lagrangians and Hamiltonians, then we get our first look at the deeper principles that are shared with the other theories in the course, with the theories that stay valid beyond our limited range of experience. But just before we can deal with those and address those issues, those methods and principles, we need to learn one new mathematical tool. The mathematics that we need to do our classical mechanics is called variational calculus, which, as the name suggests, is just a variant of normal calculus. Now, I first learnt normal calculus when my grade 8 teacher posed this problem. He said, supposing you have a very long straight wall and 80 meters of fence, and you make a rectangle with the fence, and the long length is L. How long, he said, should this L be in order to have the biggest area? Being smart cookies, we easily figured out the area. We realized that these two sides here had to be half of whatever's left. So they had to be 40 minus L on 2 long. And therefore the area was just L times that. And so what we did, of course, is we plugged in a whole bunch of numbers. And that was kind of successful because we soon discovered that L equals 40 gave us the biggest number. But it was also unsuccessful in that we never proved that L equals 40 was the correct answer. What we did was we just scattergun tried a whole bunch of numbers between 0 and 80. So how do you do this properly? Well, I made a terrible error in that I asked my father on the long ride home, we had an hour's drive home every day, about this problem, and so he taught me differential calculus. And we know now, in the safety of our university education, that all we have to do is take the derivative of this with respect to L and set it to 0. So in other words, we're going to end up with L equals 40. So it's a very simple calculation once you know calculus. Variational calculus is for a sort of generalization of this problem. And the generalization we need to understand variational calculus is very simple. Suppose we have exactly the same wall and exactly the same 80 meters of fence, but we take away the restriction that our fence has to be in a rectangle. And then what shape should that fence be in order to enclose the greatest area? Now the key thing about this, of course, is that we're not optimizing one number. We have to get every point on that fence right. And every point on that fence is, if we say start at a point, it's kind of defined by, at a given angle, it's defined by the radius of that angle. So I'm not optimizing over a number, I'm optimizing over an entire function, in this case r of theta. Another example, an even simpler example, one that we actually know the answer to in this case, is what if I have 2 points, point A and point B, and I want to know the shortest distance to get from A to B. Now, of course, we happen to know that that's a straight line, but we've never proved it. The shortest distance, so if I'm going to set this problem up, I'm going to have to think about the distance here. I'm going to break up my line into little pieces, and then my total distance, L, is just going to be the sum over all those little pieces. One of these little pieces here is going to have a length ds. So that length ds, if I just take that little piece from there, is, if I break it down into its horizontal and vertical components, easily found from Pythagoras. And if dx and dy are finite, then we can easily take out a factor of dx from that. And then it's not a big stretch, although obviously there are some niceties to observe, to take this into the continuum limit and find the functional L, which is a functional of the function y of x. And so what we're trying to do is we're trying to find the optimal function y of x that will give us a minimum value for this length L. Now, rather than solve this specific problem, what we're going to do is we're going to look at the general form for this kind of problem and show how to do that kind of optimization routine.